How's everyone doing today? Today we're going to be going over how to prove something by induction, or more specifically, how to prove a sequence of numbers, or of arithmetic I should say, by induction. So it may seem a little bit complicated, but let's just jump right into it. So first and foremost, we're all familiar with the arithmetic series, which is, if you don't know, it's the sum of 1 plus 2 plus ... plus n, which will equal n times n plus 1 over 2. Well, it's all fine and dandy that we know this right here, but how do we prove it? Well, let's get started. So the first thing you want to do is we can just assume that this is a problem denoted as P of n. And from here, we will need to do a couple things. We'll need to, step 1, prove that P of 0 or P of 1 holds true. So this is our base case. And what does that mean? It means that if we can prove that the statement holds true for inputting 0 or 1 into the statement, then we know that we can continue with our induction. So let's prove P of 1. Sometimes P of 1 will not work, but if P of 0 can work, you can still continue with the induction. But if you're given this on some exam, then usually P of 0 or P of 1 will hold true. So we're going to prove it for P of 1. So all you have to do is just plug in 1 on both sides, which in this case, if you sum all the numbers from 1 to 1, you get 1 on 1. So we'll just do 1 equals, we'll put in parentheses right here, n equals 1. 1 equals 1 times 1 plus 1 over 2. Which therefore equals 1 times 2 over 2, which will equal 1, 1. So therefore, P of 1 holds true. So I'm going to go through all the formal notation and everything on how to actually, write the proof. So you may see some notation that you haven't seen before, and that's fine. We'll go through it as we go. So let's actually prove P of 0 real quick. Let's see if that will also hold true. Well, actually, wait, no. In this case, we don't need to prove it because the arithmetic series sums from 1 to n. So we need to specify up here for all n that exist in the set of natural numbers, the set of positive natural numbers. Okay, so now that we've proven our base case still holds true, we need to make an assumption. Assume that n equals k. Namely, so right here, we'll need to take our original statement and then we'll substitute in k on both sides. So what does that mean? Well, I'll show you. So write your original statement down, 1 plus 2 plus ... plus k equals k plus 1 over 2. And that's it. All you have to do is just replace k on both sides, or replace n with k on both sides, and then this is what your assumption is. And we'll use this in our induction step, or our proof step. So let's go ahead and do that. So, induction. Prove that n equals k plus 1 holds true. Alright, so we're going to write down our original statement. 1 plus, or not our original statement, we're going to write down this statement once again. 1 plus 2 plus ... plus k. And now to add on to this, since we need to have, what we're doing with induction is we're proving that from the previous element, we can find the next element, which in this case would be k plus 1. Because the last element is k, we need to verify that k plus 1 is in this set. So we'll add that in. So k plus 1 equals, now on the right side, we need to add in, or we need to replace k with k plus 1. So all we have to do is do k plus 1, then times k plus 1 plus 1 over 2. Now, you may be wondering, where did I get all this from? From right here. Well, like I said, all you have to do is substitute in k plus 1 for k on the right side. Okay? So, now you may be wondering, well, what do I do from here? Well, it's pretty simple. Now we just need to use a little bit of algebra, and we're going to use our assumption to wrap all of this up into k plus 1 over 2. And then we're going to just rewrite it. K plus 1 equals k plus 1, k plus 2 over 2. Now, just k plus 1 is just k plus 2. That's all I did there. Okay? So, from there, what we do is we need to add these two terms together. Well, in order to do that, we need to find the greatest common denominator, which in this case, this is just over 1, so we'll need to multiply both terms by 2. So we'll do, let's see, how can I'll just write it all out. So k plus 1 plus 2 k plus 1, and all this will be over 2. And the reason for this is because we're multiplying, like I said, we're multiplying the numerator and the denominator by 2 to get the least common denominator, or the least common denominator, not the greatest. Alright, so from here, we'll have k plus 1, k plus 2 over 2. And now we can just factor everything out. So this will be k squared plus 3k plus 2 over 2. Then on the left side, I know I jumped the gun and did the right side, but that's okay. It doesn't really matter. So over here we can just do k squared plus, plus k plus 2k plus 2 over 2. And if we unwrap, or if we condense this one more time, we'll see that k squared plus 3k plus 2 over 2. And if we add these two terms, or if we combine like terms, if we combine like terms, we'll get k squared plus 3k plus 2 over 2. And we'll see that both sides are now equal. And to formally end the proof, since we're running out of space, we'll just do it over here. We need to rewrite our original statement, and I guess we can sort of write like this. So, because the left and right sides are equivalent, the induction holds true. Therefore, and we'll just write down the original statement, plus ... plus n equals n plus 1 over 2 for all n that exists in the set of natural numbers is true. Alright, so that it may seem a little complicated just doing it all at once, but we're going to walk through some more practice problems. We'll do, I think, 2 more. That should be good. And we'll make sure to do some more complicated ones, because that one was a little bit easy. Alright, so we're going to do... Okay, that bleeds so really bad. So we're going to do... Let's see. This is a good one. Alright, so prove that P of n equals 2 plus 6 plus 12 plus dot dot dot. Is it 12? Yeah, okay, it is. Plus n times n plus 1 equals n plus 1 n plus 2 over 3. So basically we're going to prove that this statement holds true. So, and I guess we can just assume that's in the set of natural positives. And actually let's okay, never mind. I just want to make sure that we specify this in the set of natural positives. Alright, so again, we're just going to do the same thing we did before. Step 1, we're going to prove that P of 1 holds true. And again, this should be the easiest step of the induction. So, you know, if your professor or whatever gives partial credit, the base case should be the easiest place to get points. All right, so how do we do that? Like I said before, we'll do 1 plus 1 equals 1 plus 1 plus 2 over 3. Then 2 equals 1 times 2 times 3 over 3, which equals 6 over 3, which is just the same as 2. So, therefore, P of 1 holds true. Alright, since we got our induction, or since we have our base case done, you could write that this is your base case. It doesn't... I mean, you should probably specify, at least in this case, I would definitely specify. But since we're just doing a tutorial, I didn't really think it'd be necessary since you already know this is your base case. But on an actual test, if you're doing it formally, then I would definitely specify this is your base case. Okay, so next step. You're going to assume that n equals k, namely, and this is where we rewrite the statement, 2 plus 6 plus 12 plus dot 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 plus k plus 1 equals k plus 1, k plus 2 over 3, and that's it for our assumption. We just replace n with k. Pretty simple. Alright, the third part, the good stuff. Prove n equals k plus 1 holds true. Alright, so we're going to write down the statement in our assumption. 2 plus 6 plus 12 plus dot 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 plus k plus 1. And now remember, we need to write down the next term, the k plus 1th term, I guess, if you really wanted to specify it like that. So what we'll do is we'll add k plus 1, k plus 1 plus 1, which is just the same as this, but we're replacing k with k plus 1. Okay? So from here, what we'll do is, if I can draw an equal sign, we'll do k plus 1, k plus 1 plus 1, k plus 1 plus 2 over 3. And again, this is just taking our assumption right side and then replacing all the k's with k plus 1. Okay? Now from here, you know that we can use our assumption to wrap all this up into k plus 1, k plus 2 over 3 plus k plus 1, k plus 2. I'm just condensing the terms to make it 14 times easier. Now we have k plus 1, k plus 2, k plus 3, all over 3. And now again, very similar to the last time, we're going to wrap up this term, or no, sorry, not wrap up that term. We're going to find the least common denominator, so we're going to multiply the numerator and the denominator by 3, which will therefore get us, we're running out of space, it's going to look nasty, equals k plus 1, k plus 2, plus 3, k plus 1, k plus 2, all over 3. And then over here, this will still equal k plus 1, k plus 2, k plus 3, all over 3. Alright, so this is where some knowledge of factoring, again, will come in handy. You really need to know your basic algebra for this stuff right here, because it can get pretty annoying if you don't know how to factor. And I'm assuming that you do know how to do this. So, on the right side, we're going to start from here first. We're just going to FOIL the right side. We're going to do k squared plus 3k plus 2 times k plus 3 over 3. And then on the left side, we're going to do k squared plus 3k plus 2 plus 3 plus k squared plus 3k plus 2 all over 3. And then here we can just distribute. So the right side will become, so it becomes k cubed plus 3k squared plus 2k. Let's see, and then distribute this in, plus 3k squared plus, let's see, 9k, and then plus, oh Lord, running out of space, plus 6, all over 3. Yeah, we're running out of space, dang it. Nah, that's fine, we can continue on another sheet if we need to. So, finally, we're going to unwrap this statement. K cubed plus 3k squared plus 2k plus 3k squared plus 9k plus 6 all over 3. Now, the thing that you can notice is that, we're just going to, well, no, we're right. I think we have enough space. So, as you can see, yeah, the left and right sides are the same now, because, we can just do, let's see, k cubed plus 6k squared plus 11k plus 6 equals k cubed plus 6k squared plus 11k plus 6. Okay, we didn't need new paper. Getting a little bit cramped, but, we're getting there. Alright, so now that the left and right sides are equal, I'll end the proof over here. So, because the left and right sides equal, n equals k plus 1 holds true. Therefore, oh Lord, 2 plus 6 plus dot 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 plus n equals n plus, or n times n plus 1 equals n plus 1, n plus 2 over 3 holds true. Good. Alright, so that's 2 proofs out of the way. And we'll do one more just because I like doing inductive proofs. But this time we're gonna go a little bit faster. We're not gonna go so slow with this one. This one may be a little bit more difficult. Okay? So we're gonna do prove that P of n equals 1 plus 2 plus dot 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 plus n squared equals 1 cubed plus 2 cubed plus dot 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 plus n cubed. Alright, so again, first thing we're going to do, and I believe this is one where, no, we can, yeah, we'll still assume that it's in the set of natural numbers, natural positives. And I don't know if I put that in the, yeah, I didn't write down the other one. That's whatever, it's fine. I didn't write down that this was in the, I didn't write this in the conclusion of the other one, but that's alright. Alright, so again, first thing we're gonna do, base case, prove P of 1 is true. This one's pretty simple. It's just 1 squared equals 1 cubed because 1 equals 1. Therefore, P of 1 is true. Alright, so we're going to assume n equals k, namely 1 plus 2 plus dot 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 plus k squared equals 1 cubed plus 2 cubed plus dot 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 plus k cubed. I apologize for my horrific handwriting. Alright, so just like before, we just replace n with k, pretty simple stuff. Alright, so prove, well actually this is the induction step, but whatever. Prove that n equals k plus 1 holds true. Alright, so lastly we're trying to rewrite our original equation. 1 plus 2 plus dot 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 plus k squared plus, now this time you may think to do something different, because I believe you could just write k plus 1 inside this parentheses and it would still be correct. But what I'm going to do is I'm going to write it outside. I'm going to do k plus 1 squared equals 1 cubed plus 2 cubed plus dot 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 plus k cubed plus k plus 1 cubed. Alright, so again, just the same basic stuff. You know, we can wrap all this up into 1 cubed plus 2 cubed plus dot 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 plus k cubed plus k plus 1 cubed, 1 cubed plus 2 cubed plus dot 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 plus k cubed plus, let's see, k plus 1 cubed. Put these in parentheses too, it doesn't really matter. And you may be thinking, oh, well, wait a second, they're already equal. And you're right, they are already equal. So at this point, you really don't need to do a whole lot because, I mean, they're already equivalent. So I guess you can just end the proof right here. And yes, I knew that this would happen for this proof. I wanted to show that just for reasons. All right. So since both sides are true, I mean, you could factor this out if you wanted. I mean, you know, it's just k plus 1 and k squared plus 2k plus 1, I believe. Just the addition of cubes or whatever it is. But let's see how much I want to end this. Oh yeah. Since the left and right right sides are equivalent. The induction holds true. Therefore, 1 plus 2 plus dot 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 plus n squared equals 1 cubed plus 2 cubed plus dot 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 plus n cubed for all n that exists in the set of natural positives. Alright, we're going to end the proof differently this time. You can do QED, you can do square, you can do a black filled in square, it doesn't really matter, it all means the same thing. But yeah, I hope this all, I can't speak English. I hope this helped all of you, and if you have any questions about my induction method or any of the symbols, just for reference, this means therefore, this means because, QED means quadrate demonstratum, which is Latin for to which has been proven, or, you know, in layman's terms, the statement has been proven. Same thing for these two, they all mean the same thing. Alright, so if you have any questions, just leave a comment, and I hope you all enjoyed. See you guys next time.